There are some important principles that we have.
Okay. So good evening everyone. Uh, Welcome to this tutorial session on materials characterization. So I'm Sabyasachi Panda. I'm a PhD scholar in the Department of Metallurgical and Materials Engineering. Hello. Am I audible?
Yes, you are audible.
Yeah. Good evening everyone. Welcome to the tutorial session on materials characterization. I'm Sabyasachi Panda, PhD scholar in the Department of Metallurgical and Materials Engineering. So I'll be taking this tutorial session. Uh, it will be a live interaction session where we'll see some of the concepts that the professor has taught throughout this week over the period of 3 videos, and then after getting a brief summary of all the concepts, then we'll go to the tutorials, some of the problems, and those problems will be not exactly but equally similar to whatever the assignments have been given to you, and I hope those problems will be helpful for solving your assignments. If anyone has any questions or any doubts, they can throughout the session they can ask without hesitance. So I hope my screen is visible to all of you.
Yes.
Okay. So this is yeah. So this as we know, the course name is materials characterization. So why in materials characterization, let's first understand why we need to do this characterization of the materials. As we know that we are living in a materialistic world, and we depend on materials, different kinds of materials, different sets of materials, and different range of materials to use in our day to day life. But whether we are designing the materials or we are applying them in a particular application, we need a certain so we need a certain things from the materials. One is the performance, another one is property, the next one is structure, and another one is processing. So these are the four different things that we need, and these things are called as structure property relationship. As we know, as a material scientist, we often talk about the structure property relationship. And what are those structure property relationship? If we see, then performance is something we define as behavior in a particular application. We design some material, or we develop some material, then why those materials fell under a certain setup condition, why the material perform extremely well under a certain setup condition that in a particular application how the material behaves, that gives us the performance. And then we talk about properties. Properties means you can say the material characteristics, what are the different, it is the, we can say it is a fingerprint of a material. Like when we apply a certain setup simulation to our material, then what kind of response the material is giving, that is what called as properties. And those different properties are can be named as mechanical property, and then electrical property, thermal property, magnetic and optical properties as well. So these are the different kinds of property that we see generally in our material. And then structure. Structure is the thing that the way we arrange things. Structure is the way we arrange things. And from atomic structure to macroscopic material, we see how the materials are arranged. So that is what called as structure. And processing is method of preparing a material, how we preparing, whether we are preparing keeping it in a equilibrium way, or we are preparing using a non-equilibrium way. So how those preparation of our material affect our structure as well as properties and performance. We see all those things in a combined way. And to check all these things like performance, property, structure and processing, we do some kind of some set of experiments or some set of analysis that is called as characterization. So since we want to know all these things, we characterize a material. And since the materials are being characterized, to study on all these subjects, that how the materials are characterized, which are the way we can characterize a material, we can know their performance, their property, and more importantly their structure, how they are arranged, we are going to see throughout this course. And some of these features that in to know about structure property relationship, to know how the materials are arranged, or we are dependent on a term called resolution. And that resolution, we will see what that resolution means. But we know that resolution is dependent on wavelength. Wavelength of what? Wavelength of different kinds of incident beams. And that beam might be a simple beam of light, that beam might be a complicated beam of electrons as well. So for resolution, we is a function of wavelength. And then if we see, there are three terminology that we generally do when we characterize the material. Three process that we take into our account. One is reflection, another one is refraction, and the last one is transmission. So how the reflection, refraction and transmission affect? Here we let's take an example of different set of atoms. Here we can see there are many atoms. For now we are considering that these will be the atoms. There are the distance between those two atoms will be d. Let's say I have a certain set of incident beam which is made up of a certain wavelength that is called as lambda. That wavelength is too much higher than the distance between these two atoms, or so it is called as if we are saying that this is the distance between two atoms, they are sitting on a plane, and that is known as the interplanar distance. So the wavelength of the incident beam is far greater than the interplanar distance. In that case, what will happen? In that case, reflection will take place, because the wavelength of my incident beam is not strong enough to resolve the distance between these two atoms. Similarly, if I have a wavelength, if I have a beam which is having wavelength lambda, and that wavelength is similar, not exactly equal but similar in the size bit of that interplanar distance d, which is the distance between two atoms which are sitting on two different plane, it is more or less similar, then what will happen? Then refraction will take place, and we'll see through through the course that what is the difference between refraction, what is the difference of scattering, what is the difference between refraction, scattering, and diffraction. So these refraction or diffraction and scattering, these three phenomena will take place when the wavelength of the incident beam lambda will be equal or similar to the interplanar distance between two atoms, or in this case I am saying two atoms. We can also say two objects. If we are not talking about atoms, we are talking about some macroscopic scale. If we are talking about, then in that case we can say that the distance between two objects, if it is d and the wavelength of my beam is lambda, then if they are more or less equal, then we can have refraction as well as the diffraction. And finally we come to transmission. Transmission means here we can see that there are two different objects or two different atoms, and here the wavelength of my beam lambda is far less than what is the interplanar distance between them. In that case, in that case my incident beam which is interacting with the material is strong enough to resolve the distance between these two. The beam will easily pass between this and will be able to resolve the distance between these two. In that case, that the phenomena of transmission takes place. Based on these three techniques, reflection, refraction, and transmission, we are going to study what kind of microscope we can build. And so reflection, based on reflection mode, we can build optical microscope, which is called as light optical microscope. Also based on diffraction, we are building, we can build in some of the cases diffraction, we can study the phase analysis, which is we can do through X-ray diffraction. And refraction also, we can in some of the microscope we can use the technique of refraction also in light microscope. We'll see how in light microscope also we can study the material. And finally comes the transmission. So for transmission, we need, if we want to resolve the distance between two atoms, then we need to go for transmission electron microscope. Then if we do not need to resolve the distance between two atoms, rather we need to resolve the distance in a very macroscopic scale or a large scale, then we can also use the transmission mode in optical microscope. And coming to the theories of light, we know that so for optical microscope, first we are going to study about the optical microscope, then scanning electron microscope or ACM, and then finally transmission electron microscope. So coming to the optical microscope is generally used by considering light as its incident beam. Light means we can say that light is made up of different photons, and photons are a quanta of energy. That means for light, we know that light is having dual nature. One is particle nature, another one is wave nature. And so from radio wave to the gamma wave, from the radio wave here and to the gamma wave, so there are different kinds of light which is available in the electromagnetic spectrum, and out of which we are able to see the visible range. So from this range to this range we are able to see generally. And then the infrared, microwave, and radio wave, they are having longer wavelength than the visible light. And UV rays, X-ray, and gamma ray, they are having shorter wavelength as compared to visible light. So light is having dual nature. Sometimes we are calling light as a stream of particles, or we can call them so here we call light as photons, and when we are talking about particle nature of light, we are mostly talking about photons. Photons means a quanta of energy. And then when we are talking about electromagnetic wave, wave nature of light, and then we are talking about two things. One is amplitude, another one is phase. So why this amplitude and phase are necessary, and why we are taking the electromagnetic the wavy nature of the light, that we have to take into consideration. So when we know the amplitude and the phase in a wave, we can at any point of time we can know when and where our incident beam is. So to define a particular set of positions at any particular time, we have introduced this wavy nature of light, so that let's say in the case of multiple beams, not a single beam but multiple beams, we can easily say that at this point of time what is the phase difference between the two beams, what is the, whether there are interference is happening or not, whether they are diffracting or not. So to take consideration of all these things, we are considering the wave nature of the light. And here the amplitude, if so let's say I am taking a wave like this. And then this is called the lambda or the wavelength, and this is called as the amplitude. Okay, so this is the wave nature of the light, where amplitude is defined and the wavelength is defined. Now coming to the studying about the duality part of the dual nature of the light. Now we'll come to the quality of the lights, like how, what are the different qualities of light that we can use in our optical microscope. So one will be monochromatic light. Monochromatic light means it is having a single wavelength. It does not have multiple wavelength. As we saw in the last picture, here we can see that when I am talking about visible light, it is having multiple, it is not a single wavelength. The visible light range is expanding from 400 nanometer, this is in nanometer scale, 400 nanometer to 750 nanometer. That means from between 350 nanometer there are different colors or different wavelength of the lights are there. So when we are talking about monochromatic light means it is having a single wavelength. That means it is having a single color. Similarly, when we are talking about polychromatic light will have multiple wavelength. That does not mean multiple wavelength will always will be in the visible range, but different shades of wavelength also can be together, and that light will be known as polychromatic light. Similarly, another thing is linearly polarized light. Linearly polarized light means the light will be traveling in a particular direction. That means if I am having a particular axis, the light will be traveling parallel to that axis. For example, so these are called, if I am taking my axis as this is my axis. If I am taking this as my axis, then all these rays, ray 1, ray 2 and ray 3, they are traveling in a particular direction, that means towards the right of the screen, but they are also parallel to the towards the optical parallel to the optical axis. So this is called as linearly polarized wave. What then comes non-polarized wave. What do you mean by non-polarized wave? Non-polarized waves are all these directions the waves will be going, and there is no particular direction. These waves will be these lights will be called as non-polarized light. That means the random direction if the light travels, then that is called as non-polarized light. Similarly, another type of another categories of light also is there, which is known as coherent light and incoherent light. Coherent light means it is having same frequency. Multiple waves, when we compare the wave nature of the light, multiple waves, they will be having same frequency, and the phase difference between them should be either 0 or constant phase difference. We should not always say that the coherent phases, the coherent beams will have 0 phase difference, but they might also have a constant phase difference. That is called coherent light. And non-coherent light is they will not have any kind of frequency. That means they will not have same frequency. That means some random frequency they will have, and the phase difference will be there. We should not say that the 0 phase difference will be there. Then in that case the waves will become the coherent wave. But the phase difference should be, there is no definite relationship between all those phase difference. So that means there will be random phase difference between all these waves. And then the collimated collimated lights are, they are also going in a particular directions. They are traveling straight in a straight path, but in a particular they are traveling in a straight path. It might not be parallel to the optical axis. It need not to be parallel to the optical axis, but they should be traveling in a straight path. However, divergent means, as we know, all these divergent convergent lens and divergent lens. Here, if I am putting a screen here, then we can trace their paths. That I might be able to collect all these rays in this screen. Let's say screen is S. I might be able to collect all these rays in this screen, but they are not. They might be polarized one. That means they are having a certain set of directions. They might not be linearly polarized, but a polarized one. That means they might be having a certain rule that they have to travel within a certain range, but they are diverging towards each other. That means at this screen they will not meet each other. It's like even if they meet, they will only meet at the source. Let's say this is their source. Okay, so source I have let's say SO. So this is their source. They will only meet at the source, not anywhere along the path. Okay, so this is the collimated difference between collimated and divergent beam. The use of collimated and divergent beam are extremely used when we are talking about X-ray diffraction, because there we will see that when the X-ray comes, when the light comes, you cannot restrict the light to travel in one direction. Light will always travel in three-dimensional direction. Though we are drawing that the light will be traveling on a two-dimensional paper, we are drawing that line will be traveling in a particular direction. But in real application, when light or any kind of beam, when they come out, they will always travel in a conical direction. So in a three-dimensional direction. So we cannot restrict that. So what we do, from that conical direction, we put certain set of collimated slit kind of thing, which will restrict the light to travel in all 360 direction. Rather, they will again start traveling in a particular direction. So these collimated lens and divergent lens are extremely useful in X-ray diffraction. Monochromatic light is extremely useful in transmission electron microscopy. Transmission electron microscopy, we do not use the light term. There the incident beam is made up of electrons, but we are this monochromatic means certain a particular wavelength, and particular wavelength the electrons are having a particular constant wavelength. We accelerated them to a constant energy, because energy and wavelength they are related to each other. So this monochromatic this thing is used exclusively in scanning electron microscopy as well as transmission electron microscopy. Polychromatic we are using in light microscope, because different to see different kind of things we need this polychromatic light. And now the optical microscope are also equipped with monochromatic light. One kind of like different color if you want to see, then we can also see those things. And most importantly, the coherent and non-coherent in X-ray diffraction, the coherency is important, because otherwise we will not get the diffraction spots. If we don't get the diffraction, if we do not use the coherent beams, we will not get the diffraction spots, and hence we will not be able to see different kinds of peak and the position. We cannot distinguish their positions. Okay, just give me 1 minute. I'm not sure what is some problem is occurring. I'll be back. I'm just stopping this presentation. Just give me 1 minute. Yeah, sorry for the delay. There was some issue with the presentation. Okay. Yeah. Now the screen is visible, right? The whole screen.
Yes, sir. Yes, sir.
Okay. Thank you. So now we will see the properties of light. So now that we have talked about the quality of light, how different kinds of light we can use, we will talk about the properties of light. And from the properties of light, we can say that here we are seeing c. C means the velocity of light in in air medium. Okay, because generally we consider that velocity of light in the air, and this is given by v into lambda. So here the v is not v, this is called the nu, and this nu is known as, sorry, this nu is known as the frequency. Okay, so this nu is the frequency and lambda is known as the wavelength. Since we are talking about properties of light, so here you can say the wavelength of light. Okay, so the speed of light in air medium is given by the frequency of light and wavelength of the light. And similarly, the energy, the E, will be given by h into nu. Here h is the Planck's constant, as we know, and nu is the frequency of the of the light. And if so, this is, let's say, I am taking as my equation 1, and this is I am taking as my equation 2, substituting equation 1 in my equation 2. So here E is equal to h into nu. So instead of nu, if I want to put this nu is equal to c by lambda from this equation. If I want to put c by lambda, then I will have the as E is equal to hc by lambda. So this equation, the E, that means the energy of my light, of my incident beam, will be directly proportional to the speed of light, because here I am talking about the light, will be directly proportional to the speed of light and inversely proportional to the wavelength, right? So here I got to know one relation, that E will be inversely proportional to the wavelength of my, the energy will be inversely proportional to the wavelength of my incident beam. In this case, my incident beam is light, visible light, so that is why I'll say that the energy will be inversely proportional to the wavelength of the incident beam. And then there are two different terms when it comes to any kind of characterization instrument. When we talk about that, one will be intensity, another one will be brightness. Generally intensity and brightness, people get confused between that. Intensity and brightness, they might be equal, but in certain cases intensity and brightness are not equal. Why? Because intensity is photon count per second. When this intensity, when we talk about this thing, photon count per second means how much photons our, if I'm putting a detector, and from a source, let's say this is my source, and so this is my screen, I'm sending all these rays. Okay, but my screen limit is up to this, but I am sending all these rays, and these rays will be going in all directions, but my screen will only capture these 4 rays, right? So that means, though I am sending much many these rays, but my screen is able to capture only these 4 rays. So that means whatever the intensity I will get from my I will get, so those intensity will be consisting of on these 4 rays only, right? So that is why this intensity is photon count per second. Since why I'm talking about this photon count now, because I'm considering the particle nature of light, and in particle nature of light, photons are the quanta of energy, right? So that is why photon count per second is intensity. Then comes brightness. The brightness is beam density per solid angle. And here, what do I mean by the beam density? The density, when the term comes density, that means I am considering a particular set of area, right? And beam density per unit solid angle. That means if my source is like this and it is giving the rays in this directions, here it is we can see this is a two dimension, but when I am taking this two dimensional object into three dimensions, then this will become a cone kind of structure, a conical structure. So in conical structure, if we see the instead of now, if I am saying that this angle is, let's say, theta, this is a two dimensional angle because I can only draw a two dimensional angle here. But if we rotate that two dimensional theta angle all over the if we rotate that theta, taking, let's say, this line is inside that cone, and around this line, if we rotate this whole cone itself, or in this case these two lines only, then we will get a completely conical structure. So that total angle is known as the solid angle. And here the beam density per unit solid angle means, so that means if I have to draw it more specifically, let's say, so this is the back side of this cone. This dotted angle is taken from back side of the cone, and this angle is the front side of the cone. As I said, when we let's say this is my the source where the lights are coming. The lights will be coming in all directions. So the whole total angle that my light is coming out, that is known as the solid angle, and the brightness is defined as beam density per solid angle, right? That means the measure of how many photons per second can be directed at a given area of the specimen. If my area is like this much, let's say my area, my specimen is this big, but my area, I want to map this area. So in this area, how many photons per second will be directed? If we are able to direct large number of photons, then that will be a high bright image, that will be a much brighter image. But if we are not able to direct many photons towards this area, then the brightness will come down. So based on that, we will have, or we are able to see whether the our image is bright or image is not bright. And generally this brightness, the unit of this brightness is called as B, and the unit of this brightness is given as in case of this brightness, when we are talking about the electron, let's say my beam is of I am talking about the brightness of an electron gone, let's say, and in electron gun, the electrons are coming out. So in that case, the how do I measure the electron? I will measure the electrons by the number of by the amount of current that they generate in my detector, in my CCD, like charge coupling device. So that is A into meter square, and this is SR. So this SR is known as ampere per meter square into SR. This SR minus 1, this SR is known as, this is a term called, this is the term, because generally in two dimension, when we talk about the angle, we talk about theta or any theta or alpha or sigma, we give some angle. In three dimension, the unit of those angles will we are giving radian, or we are giving degree. We give like that. In three dimensional, when we are talking about the angle, that unit is given as star radian. So this, the brightness, the unit of this brightness when we are talking about a beam of electrons, that will be given by ampere per meter square into star radian. That means image beam density per unit solid angle. Okay, so how many photons we are able to direct towards our specimen. Then comes reflection and refraction of light. We know that reflection, that is, this is the incident beam, and this is the reflected beam. Okay, and this is the incident angle, and this is the refracted angle. And when we will be getting, and this is our object, and reflection, remember reflection happen, let's say the incident beam wavelength is lambda, and reflection will only happen when this distance, interplanar distance, I am taking it as d. Reflection will happen when lambda will be very, very larger than d. That means my wavelength, my beam is not able to resolve the distance, the interplanar distance, or any the distance between two objects. So this is the condition when reflection happen. And if I am assuming first that the incident beam, this is the normal, the incident beam, the normal, and the reflected beam, they are coplanar in nature, then how the reflection will take place? The angle of incidence will be equal to the angle of reflectance. Okay, so here this is the reflection of light. Then we will see the refraction of light. Refraction will happen same. If I am talking, this is my incident beam, and I am saying that it is of wavelength lambda, and it is having distance, some distance d, and if lambda will be equal or similar to the distance, then in that case refraction will happen. Okay, and refraction, so this is the angle of incidence, and after this is n1, that means the refractive index of our medium, and here this is refractive index of another medium. So there are two mediums involved in refraction. However, there is only one medium involved in reflection. Here there are two medium. So this is alpha 1, if we say our angle of incidence, and here the angle of refraction will be alpha 2. And by Snell's law, we know that n1 sine alpha 1 is equal to n2 sine alpha 2, and then we can write this equation: n2 by n1 is equal to sine alpha 1 by sine alpha 2. Okay, so this is the laws of reflection and refraction. And here there is another term called index of refraction of substance, or we generally know it as refractive index. So refractive index of any substance will be given by speed of light in air. Let's say speed of light in air, I am giving it as c naught. This is the speed of light. And speed of light in substance, speed of light in substance, I am writing it as cs. Then this is the refractive index of any material or any substance. Okay, now we will come to the image formation in a lens system. So if I am talking about a lens, let's say this is my principal focal point, and this distance is f. Same for this. I am putting an image here. Then what will happen? The parallel rays will be going through the focus. Okay, and the rays which will be going through the focus, they will be going undeviated, right? And the rays uh, which will be going the rays which will be going through the origin. So these are the rays which are going through the origin, they will be going undeviated. The rays which will be going through the focus after refraction, they will be going parallel to the, this is my optic axis, they will be going parallel to the optic axis. So here comes my image. Let's say I am giving image as AB, so here the image name I am giving it as A dot B dot, right? So if this is the image formation in a simple lens system. If I am talking about if I want to know at what distance my object will be, at what distance my image will be formed, because what I need to do, I cannot put a simple object here and then a lens and then leave. I need to put something so that I will collect my image. So this where I will put my detector, this is known as the image plane, right? Here in this image plane I will put my detector, whether it's a solid state detector or it is a silicon lithium detector. So I have to put the detector so that I will get my image. So this is the if I want to quantify this thing, then there is a law which that is known as, so if I am saying that my object distance is u and my image distance will be v and my focal point distance is f, then the law says that 1 by f is equal to 1 by u plus 1 by v. Okay, so based on this formula, we will derive later how the magnification works, how we can substitute object distance and image distance in a set of equation. And this is a simple lens system, a single lens, and this is a compound lens system. Here we can see the compound lens system, what did it do. This is my object, right? And this is my first lens. This is my object and this is my first lens. Here the first image is created at this point. So this is, I will call as my intermediate image. But now, so the size of my first size of my object will be similar to size of my intermediate image. But when I use this intermediate image as my second object, or not as a second object but as a intermediate object for my second lens, then what is happening, and the lens is bigger than the first lens, then what I am getting, my object size is this much, but I am getting an image size is a very, let's say this size is h, this is h bar, I can see that h bar is larger than h. So this is how, so I got to know that that if we can put multiple set of lenses, so we will be seeing a much larger image than what we will see if we put a single image, right? So that is the reason behind a compound lens system. We got to know that if we can use multiple sets of lenses in a single system, then we will get a large magnification, we will get a larger magnification. Then you can ask, then why don't, let's say I want to this magnification is 50x, this magnification is 20x, so combinedly the magnification, as we will see further, the total magnification will be 1000x, right? Then 5, and this is based we have not used any kind of special incident beam, we are just using light. Let's say these rays are coming from light, then why we cannot use, let's say for now we have used 2 lenses, why we cannot use 4 lenses, why we cannot use 5 lenses, why we cannot use 10 lenses. Each lens, if it is having 10x magnification, imagine 10 times 10x magnification, then we will be getting a much larger magnified image as only by combining many lenses. But we can get all those images, theoretically we should get those images, but there is practical limitation to this theory. What practical limitation? All these lenses, optical lenses, they are having some set of aberration or called defects, which we will study in next week. These are These are the things which is limiting us to use multiple lenses. We cannot use 10 12 lenses, and also the complexity of the system increases if we use 3 4 or 5 6 lenses. More than that complexity, first thing, and the main thing is, due to this lens defects or lens aberration, our magnification we might be getting all these things, but we will not be able to get a higher resolution. For a microscope is more than magnification, resolution matters most, because through our resolution only we can see any kind of image. If our resolution is good of our microscope, then we will be able to distinguish different points, different lines, different set of features. But if our resolution is not good, no matter how much magnification we go, we will not be able to get a good image. So that is the reason behind why we are not using 10 or many number of lenses. Instead we are using a certain set of lenses, and then when we need to see very in a micro scale or in a nano scale, why we are switching our incident beam from light to electron rather than using a infinite number of optical lens, right? So this is the lens equation that I was talking about. 1 by f is equal to 1 by u plus 1 by v, and this in this lens equation there is the term called magnification. Magnification is given by the ratio of image distance to that of ratio of object distance. Okay, so now if we substitute here in the equation, we will get two sets of we will be getting the magnification in two terms. One will be in here the focal length and object distance, and then here focal length image distance. Okay, and so here we can see the v minus f divided by f. So same thing, if I am substituting, so m is equal to v minus f divided by f. Now for an objective lens, if I do, then MO is equal to VO minus FO by FO for eyepiece. That means for the condenser lens, because the condenser lens will be, and there are typically two types of lenses which are used in a microscope. One will be condenser lens, another one will be objective lens. Remember, always condenser lens will be staying closer to the
Sure.
yes. Hello.
Ah, Previously your screen is not visible. Now visible, sir. Okay,
Okay.
carry on, sir.
Yeah.
Sorry.
So the so there will be two sets of lenses will be there. One will be condenser lens and another one will be objective lens, and that in the magnification of that objective lens will be given by V naught minus F naught by F naught. And for eyepiece or the condenser lens, the condenser lens will be staying in optical microscope. The condenser lens will be staying close to the source of illumination, and the objective lens will be staying close to the detector. But that thing will be changed in when we switch from optical microscope to electron microscope. In electron microscope, the object will be the objective lens, same concept will be there, but the different the path, the construction mechanism will be different, but the principle will be same. Like the condenser lens will always stay close to the source of illumination or the incident beam, and the objective lens will always stay closer to the image plane or towards the detector. And if we include this is a condenser lens, this is the eyepiece, the objective, and if we are trying to because we need some kind of space when we are seeing in an optical microscope, we need some kind of space so that our eyes will be comfortable seeing those things. So for that we will also introduce another thing that is called tube lens. So there are different kinds of tubes are also there. So based on that we are getting this thing. The total magnification will be given by m naught into me into mt. That means the magnification will always be multiplied, not added. That is the thing to remember here. Whatever, no matter how many number of lenses you use, always the magnification will be added. And from here, let's say I use two different set of lens, and in this, from this equation, if I'm taking m is equal to m1 and m2, let's say I have two different lenses which whose magnification is m1 and m2, and in terms of the image distance, if I write v1 minus uh, f1 divided by f1 into v2 minus f2 divided by f2. Okay, so if I have to write in terms of this thing, then I can also write like this, or similarly you can also write in terms of focal length and the object distance, right? And then comes diffraction and interference. Okay, so in general way, in the simplest way, diffraction is the spreading of light when a beam interacts with an object with similar size, that I told regarding refraction. Okay, so here the simple concept of diffraction is the spreading of light when a beam, that means let's say my beam is coming like this, and I'm keeping my object here. These are the obstacle, and only from here to here, these are the path. So when I, let's say my beam is, so this is lambda and this difference is d, and I'm saying that lambda will be similar to d, then what will happen here, it will spread, and same thing will happen also from here, it will spread. Okay, I am showing it in this direction like this, but also these if we consider the phase and amplitude of this thing and the wavy nature of this light, then how it will spread, I will show. So this will be spreading, so this is I'm showing all these things here, these things I'm showing it here. So how they will start spreading, they will spread in waves. Okay, and here at this point these two waves met with each other. Now this will be another source, and from here also the waves will be spreading, and now I want to see what is happening, right? So I have put a screen, this is not a screen. Okay, this is just a section, so this is a screen, I am putting it here. If I want to see what is happening, then in 3 dimension what will happen, actually the thing that takes place is interference. Interference, what do you mean by interference? Summation of 2 or more superimposed waves. Okay, and interference pattern looks like this. You can see in central spot there is a bright maxima, and then after that a dark thing is there, that means alternative pattern of bright dark, bright dark, bright dark rings are there. So this is what we call as interference pattern, and this interference pattern are of two types. This interference, when the interference happens, this is of two types. One will be constructive interference, one will be destructive interference. What is constructive interference? Constructive interference means, let's say one of my wave is going like this, another of my wave is also going like this. So that means if I am taking a point, if I am observing at this section, and this point, let's say P, and this point Q, they both are in same phase, the phase difference is same, and their amplitude is also same. That means here the constructive interference will happen, they will not eliminate each other. But similarly, to opposite to that, when I will have a wave something like this, then combination, let's say this is 1, this is 2, and this is 3, so I will get a constructive interference 1 plus 2, but I will get a destructive interference 1 plus 3. What will happen, since they are 1 and 3, their amplitude are equal, and I am considering that their amplitude will be equal, what will happen, the 1 wave and the 3 wave, they start eliminating each other. So plus 1 minus 1, that will give us the 0. So that is why all these dark spots you are seeing in this different interference pattern, all these dark spot they generate. So this is due to the destructive interference. And when the interference takes place, and all the there is a set of rules that when we will see the Bragg's diffraction, in X-ray Bragg's law in X-ray diffraction, this constructive interference only will give us the set of diffraction. Okay. And now coming to the Abbes criterion, we will see that for a lens to form an image, at least two diffracted beams should enter the objective lens and allowed to recombine in the image plane. Here we can say that instead of diffracted, we can also say refracted beam, because we are putting here the objective lens is here and all the beams are refracted. Now there is an interesting thing to notice here. You can see, let first consider this O1 point. Okay, let's say this from O1 point there are three different beams are going, this one, and this one, and this is object 1, and the object 1, the image of this one point is only found when all these three are combined, right? So that is why at least two of the refracted beams should enter the objective lens and allowed to recombine. First they have to enter and then allowed to recombine, then only they will get there will be the formation of image. If I am putting my detector here, then in the image plane itself, then what I will get? I will get the image of I1. I will get the I1, that is the image of O1, right? So that means for me to get an image, all the beams which are coming for me to get an image of a particular object, all the beams which are coming out of that object should recombine in the image plane, right? But if you look at from another angle, look at these things. Three different beams, but they are parallel to each other. Three different beams, they are parallel to each other. Why three different beams? Because they are coming from three different objects, right? But they are parallel to each other. When they recombine, they are not recombining in the image plane, rather they are recombining in another plane. That plane is known as back focal plane, right? Here I will not get information about my image, but I will get, if I put a detector in this plane, then I will get the information about these spots, this F1 spot, F0 spot and F1 spot, and these spots are called as diffracted spot. And this pattern is known as diffraction. And this is this phenomena that take place in back focal plane. Okay, so based on which information I want to see, I will keep my detector in that. If I want to see the image, then I will allow all the rays which are coming out of my object to recombine in the image plane. If I do not want to see the image, rather I want to see all the similar type of rays which are coming out of the object, not all the rays, all the similar type of ray. That means these three rays, 1, 2 and 3, they are all parallel, though they are coming from different places, but they are all parallel. Though that's why these similar type of ray, if I want to see, and what are their orientation relationship and what are their spacing relationship, if I want to see, then I will put my detector in another plane that is called as back focal plane to collect the diffracted spot, and the pattern of that diffracted spot is known as the diffraction pattern. Okay, and this is the diffraction pattern, and this diffraction pattern is collected from this back focal plane, not from the image plane, right? So this this is a diffraction pattern, and this is how a diffraction pattern looks like. Unfortunately, these things we will not be able to get in optical microscope. To get a diffraction pattern, we need to go to high resolution scanning electron microscope, or generally we use the transmission electron microscope. And here if we see, so there are different kinds of spots are there. So these spots will be, the diffraction pattern of a spot is given by a single crystal. When your material is single crystal, then the diffraction pattern will be spots. When your material is polycrystalline, that means the many grain orientation will be there, then the diffraction pattern will be rings, and those rings will be concentric. Like you will get like this, and then like this, like this. Instead of getting one spot kind of thing, you will get these concentric rings. Okay, and here from diffraction pattern, what we are observing is the spacing between the grid here we can see the grid spacing 0.25, the grid spacing 0.125, the grid spacing 0. As the grid spacing decreases from A to B to C to D, the spacing between the diffraction pattern increases. Why it happens? Because these patterns are generally, these diffraction patterns, they are generally taken in reciprocal space. So we are dealing in real space, and there's diffraction patterns are taken in reciprocal space, which we'll study. So that is why there is the inverse relationship between the grid spacing and this diffraction spots spacing. So this is the inverse relationship it is having, grid spacing against the diffraction spot spacing. And this is a 2D crystal. This thing is a pattern, the diffraction pattern of a 2D crystal, not in a 3-dimensional crystal. So this is what the diffraction pattern is all about. And then comes resolution. The resolution is the smallest separating distance between two distinct points. That's what generally a microscopist always looks for. And this resolution is given by Abbe's criteria, which is known as lambda by 2Na. And here Na refers to the numerical aperture. What is numerical aperture? Numerical aperture is the light gathering capacity of a lens. Whether it's an optical lens, whether it's an electromagnetic lens, or any kind of lens, it is the light grasping or gathering power. And here lambda is the wavelength. As we can see, the intensity here is unresolved and just resolved according to Rayleigh criterion. So there are two criterion actually. One is Abbe's criterion, another one is Rayleigh criteria. The Rayleigh criteria gives us the theoretical limit to which we can design our instrument. Okay, and what does Rayleigh criteria say? It says that two adjacent objects are defined as resolved when the central diffraction spot of one point coincides with the first diffraction minimum. Here we can see the maximum of this point, that is the central bright spot or the central diffracted spot, it is coinciding with the first minima of the other point. Then this thing is just resolved, and this intensity there will be a dip in the intensity, and the dip in the intensity is, let's say this is my Imax, and this height is 0.8 of Imax. Okay, so this is what Rayleigh criteria is. And so Abbe's criteria, remember, lambda by 2Na, where Na is the numerical aperture, and we'll see what the numerical aperture is a dimensionless number always, and it characterizes the range of angles. That means from here to here, all the rays which will be going, they will be going through this lens, right? No matter how many rays you send, but the moment some rays are going from like this, that those rays will not be going through this lens, and hence they will be simply going away. So this lens does not have power to collect all these rays, but rather this amount of rays the lens will be collecting. So that is why if I am talking about, this is the alpha. Always also remember, there is always confusion between alpha and 2 alpha. Generally in numerical aperture, the formula, it is n sin alpha. Alpha is the always semi apex angle, or sometimes also it is called semi cone angle, because it is making a conical structure. Okay. So you should see that the semi apex angle or semi cone angle, and here the n is the refractive index of the medium. Okay, and this is what numerical aperture is. And the path difference, how the path difference of two different light affects the numerical, how the resolution affects the resolution limit, we'll see. Let's say this is plane and this is another. So this distance, let's say D, and this is I, right, and this is R. Since we are considering reflection, that means I is equal to R for now. And now the what should be the path difference between these. Let's say this is my wave, my light 1, and this is my 2 different incident beam 1 and beam 2. So what should be the, I told a few slides back that for us to get a diffraction pattern, there should be constructive interference, right? So how the constructive interference will happen? The constructive interference will happen when the path difference between beam 1 and beam 2 will be equal to or integer multiple of lambda. What is lambda? Lambda will be the wavelength. Okay, so integer multiple of lambda, if it happens or equal to the wavelength, then only constructive interference will take place, and when constructive interference will take place, the diffraction pattern will get. Okay, so that is the rule. And here let's say this is A, this is B, and this distance is D. If I am to draw a perpendicular to here, this is C, and if I am to draw a perpendicular on this path, that is D. Now if we can see here, my beam 1 and beam 2, beam 2 is obviously traveling much distance, but how much distance its beam 2 is traveling? Up to this C point, up to this point, the amount of path traveled by beam 1 and beam 2, they both are equal because that is a perpendicular. And after point D, so this is let's say 1 bar and this is 2 bar, 2 dash. After point D, the amount of path traveled by my this beam 2 dash and my beam 1 dash, they are similar. So whatever number of path difference is there between beam 1 and beam 2, those are between CB and BD. That means I can write the path difference is BC plus BD. So this extra path is traveled by beam 2. So if this path difference will be equal to, that means wavelength lambda or an integer multiple of wavelength, then what I will have? I will have constructive interference. Once I get constructive interference, I will be able to get diffraction pattern. Okay, so this path difference. So now if we consider BC, this is a ACD triangle in ACD, ACB. ACB. AB is the hypotenuse because AB is equal to D. So ACD, AB by, this is I, this is 90 minus I, this is I. This, so what will be? This is I think I, yes, and this is R. Just look carefully, this is a little bit clumsy. So AB, not AB, what is that? Sorry. Okay, in triangle ABC, so the path difference is given by BC, right? Okay, this will be the I, since this is I, this will be the I, this is 90 minus I, sorry, this is I and this is R. Okay, so this is I, not this one. In triangle ABC, BC by AB is equal to sin I. Similarly, in triangle ABD, BD by AB is equal to sin R. So if you take BD here, that will be AB sin R. If you take BC from here, that will be AB sin I. That means the path difference will be BC plus BD. BC is AB sin I. This is simple geometry, trigonometry I am just applying. This is AB sin R, right? So AB sin I, AB sin R, in I have already assumed that I is equal to R. That means AB to AB sin I, or sin R, anything you can put. The value of AB is D, 2D sin I. If I am talking now that I R, if I take all these things equal to alpha, then the path difference will be 2D sin alpha, right? And 2d sine alpha. Now I have said that the path difference is 2d sine alpha, which will be equal to wavelength this lambda. So I can write lambda is equal to 2d sine alpha, and from here I can write d is equal to lambda by 2 sine alpha. I can write that. And if so this can be derived, d is equal to lambda by 2 sine alpha, and then I am saying that, let's say I have some refractive, my medium is having some refractive index. In that case my lambda n will be lambda by n. In that case I can write d is equal to lambda by 2n sine alpha, or I can write lambda by 2n sine alpha is given by 2na. So from here the Abbe's criterion has been derived based on the path difference. Okay, this is na, 2na. Okay, so this is how the path difference between two beams are calculated. So the path difference between beam 1 and beam 2 should be either equal to wavelength or integer multiple of wavelength. What will happen when the path difference will be integer multiple of wavelength? When that thing will happen, the constructive interference will take place. From the constructive interference, the diffraction will take place, and that is how we have decided our resolution limit. This d is according to, so the previous d is, this is the Abbe's criterion, but now we'll consider the Rayleigh's criterion for our resolution limit, because that is the theoretical one, and that resolution limit is given by 0.61 into na. Na is so numerical aperture, and it is given by n sine alpha, where alpha is the semi-apex angle, and n is the refractive index. Similarly, when condenser numerical aperture will be less than objective numerical aperture, 1.22 lambda divided by condenser numerical aperture plus objective numerical aperture, right? And this image brightness, there are some other terminologies also are there, how the image brightness is related to numerical aperture as well as magnification in different mode. One is trans illumination mode, another one is epi illumination mode. So this image brightness formulas are there. And then comes useful magnification. What do we mean by useful magnification? Not all the magnification will be useful, because just like the magnification we can correlate when we are using our mobile phone with one feature called zoom feature. Like when we are zooming one picture, we can only see distinct points or up to a certain magnification. Beyond that, even if we zoom it, will not be able to distinguish. So that is what the useful magnification is. In this picture, when we are going to 40x magnification, we can still see features. 600 we can still see features. 1200 we can still see that these are the lines, these are white line, these are dark line, we can see. And even in 2400 magnification we are going, we are able to see like this is a dark area, or this is some kind of step is there, this is a bright area, this is a normal area, we can see. But let's take another example. In this case, let's say this is a TM image. Here this image is of 1x magnification, but I want to see it the 2x magnification. I am still able to see the difference between, like this is a dark line and this is a bright line. I can still see the difference. But if I further zoom it from 2x to 10x, I can still go for higher magnification, but I am not able to distinguish between the dark lines and the bright lines. I cannot completely distinguish. I can see that this is bright, this is dark, and this is some gray area, but I cannot distinguish what are the features are there, right? And similarly, from 10x if I go to 30x, I'm not able to see any of the features. So that means useful magnification is not it's not the total magnification, rather 500 to 1000 of the numerical aperture of the objective is called as useful magnification. Otherwise, all these magnification from 2x to 10x to 30x, these magnifications are called as empty magnification. Though I am going higher in the magnification mode, but I am not able to get useful information. So what is happening? Excessive magnification I am only doing, and the image quality is degrading. So that is the difference between total magnification and useful magnification. And then comes another term that is called depth of field. this depth of field always related to the specimen side. That means, so this is my object. When I'm keeping in front of lens, I'm getting some kind of image, right? But let's say I want to keep my object here. Whether I will get the image in the whether I will be able to get the image with sharpness or not, that is my query. Whether I will be able to get the image with sharpness without any loss of my image quality, whether I am able to get it, that, and in which range. Let's say any range between these two. If I move my image anywhere between these two, I'm still able to get, I will not be getting the image at the exact place. I'll be getting the image little bit here and there, either to right or to the left of where I am getting, but still the sharpness is not decreasing that much. The contrast is still there, so that I can identify that these things are happening. And if between these range I can move my object with when my image is not degrading, that range is total called as depth of field. And depth of field is always related to specimen, not related to the image, right? And similarly, and the depth of the formula for depth of field is given by n lambda divided by na square. This if we, n lambda is equal to n sine alpha, this is square, n lambda is equal to n square sine square alpha. And remember one thing, I am writing n here, okay, but this n is this is not this n is related to the refractive index. This is not refractive index, this n, this is some sort of number you can assume. No. No, this is also refractive index, sorry. So you can cut this thing nn, and you will finally get the lambda by n sine square alpha. This is the formula for depth of field, but you have to remember this thing, n lambda by numerical aperture square, okay. And then depth of focus, people always get confused between depth of field and depth of focus. Depth of field is always related to the specimen. Similarly, the depth of focus will be always related to the image which we are going to get using our detector. So the range of position within which the image can be viewed, that means even if I put my detector at this place, I'll be able to get the image. If I put my detector at this place, still I'll be able to get the image. I'll not get the exact on the correct image, but there will be a little bit changes, but changes in the image I will get based on the least of based on the disk of least confusion. There is a term called disk of least confusion. So based on this criteria, I will have to select whether I am getting my depth of focus is correct or not, okay. Then comes a terminology called field of view. Field of view and the diameter of the objective field of view index is known as S. So this is what the field of view is. If I am putting all these things like this is S by 2 and this is another S by 2. So in total in this range I am getting my image. So this is called as field of view, okay, and the index is noted as S. And the diameter of the objective field, if I am talking about the diameter of the objective field, then that is called as S by M. That is, this S is the field of view here, and this M is the magnification. Remember earlier we used to write the magnification of the objective lens is M naught. Here also same thing, the magnification of the objective lens. It's just a change of terminology, nothing more, okay. And this angle is known as sigma by 2, and this sigma is called as angle of view. So this is field of view, this angle is known as angle of view, and this is, if I am going to draw like that, this is a straight line, okay. This is in total this is sigma, and this is sigma by 2. So you can from the geometry we can see that tan sigma by 2 is equal to S by 2, and this is the object the focal length of the eyepiece. So we will get tan sigma by 2 is equal to S by 2 Fe. Right, this is about field of view and angle of view. And so these are the terminology. And yeah, now you try to solve what is the time now? Okay, just take 1 minute. Now all the concepts are revised, like we have all gone through all the summary of whatever the professor has taught. So now we'll solve some sample problem. So this there are 5-6 problems are there. You take 1 minute, and so this is the problem number 1. I'm reading if anyone is not able to see the screen. So find the numerical aperture and resolution limit for light having a wavelength of 700 nanometer in pure water, where mu, this mu is refractive index, is 1.33 at cone angle of 70. So this is the problem. You take 1 minute and then try to solve, after which I'll solve it. Am I audible or no?
Yes, clearly audible.
Okay, yeah. So you can take 1 minute and then try to solve. I'll solve it afterwards. Okay, so we'll see the solution of it. So the question is, find the numerical aperture and resolution limit, and the given parameters are wavelength. That means lambda is given 700 nanometer. If I am considering 700 nanometer, then I can say that this is 0.7 micrometer, right? And the other thing that is given, mu. Generally we we say the refractive index of medium, where our beam of light is coming, that is termed as n or mu. So this mu is the refractive index. Okay, and here there is one thing which I talked about earlier. That thing is called as cone angle. So the moment we say we see angle, we should not by default think that it is they have given alpha. Rather, they have given the cone angle, means this is 2 alpha. The total angle they have given here, 2 alpha they have given. But for our purposes, when we know that the resolution limit is, theoretical resolution limit is given by Rayleigh's criteria, right? So Rayleigh's criteria, if we talk about the resolution limit, then D is equal to 0.61 lambda divided by numerical aperture, right? Okay, and from here wavelength they have given, and first we have to calculate the, so here there are two variable. One is D, the resolution limit, another one is Na, numerical aperture. So first we have to calculate the numerical aperture. What is the formula for numerical aperture? N sin alpha. Here alpha is the semi-apex angle or semi-cone angle. N is the refractive index. So refractive index is given, as well as the semi-apex angle is also given. So 2 alpha is equal to 70 degree. That means alpha is equal to 35 degree. Okay. So here we will put n is equal to 1.33 into sine 35 degree if you calculate, that value come close to zero point 0.7 or some micron, that value if you calculate, so you will get numerical aperture value. Putting that numerical aperture value, if you because here 0.61 into lambda value we know already 700 nanometer, which is 0.7 micrometer. I'm taking all the values in micrometer. 0.7 micrometer divided by numerical aperture, also that value will be in micrometer. So from here you will be able to calculate the resolution limit. Okay, has anyone calculated the resolution limit? It would be coming close to, I think, 550 nanometer or something. Has anyone calculated?
561.
560, yeah, that is the correct one. 560 nanometer. Yeah. Okay, so we'll go to the next problem. So this is an easy problem. For an optical microscope, the focal length of the objective lens is 40 millimeter. Focal length of the eyepiece is 10 millimeter. Total magnification is 50x, and find the optical tube length if the distance of the distinct vision is 100 millimeter. We have not gone through this concept actually. Actually, I have told the expressions, but I have not told the exact expression. Let's try. Take 1 minute and try to solve it. Then I'll solve it. Okay, so we'll solve it. So what are the things that they have given? The focal length of objective lens f4 they have given 40 mm, and focal length of eyepiece they have given 10 mm, and the total magnification they have given 50x. Find the optical tube length if the distance of distinct vision. The distance of distinct vision means uh, like how far from your own eyes you are keeping, you are viewing the things, or you are keeping the material to be viewed. Okay, and so we know that the magnification is total magnification they have given. So total magnification is magnification of objective into magnification of eyepiece. So what is the formula for magnification of objective? Magnification of objective is v naught minus f naught divided by f naught, right, into same thing v naught, but magnification of eyepiece, if I am talking about, it is be plus fe. Why? Because object and eyepiece are the where the object is situated and the image is formed, they are in an opposite direction. So once you take one direction as your positive, and from the origin the opposite direction will be taken as negative. So this is this, and here we have given one term v naught minus f naught. We have talked about the optical tube length. Okay, and ve plus fe we have talked about, we have named it distance of distinct vision, right? So when we see and this is given as t, and this v plus it is given as d, right? So this formula, this whole am formula now coming to t divided by f naught into d divided by fe. So what are the things that they have given? M they have given is 50 is equal to t optical tube length. This is what they are asking. So t into d, distance they have given 100, divided by what are the things that they are asking? F not fe, 40 into 10, right? So 10, this is gone, 10, 44. So now t coming to 200 millimeter. Okay, so the optical tube length will be 200 millimeters. So remember this formula. I'm writing it again here. M is equal to T D divided by F naught into Fe. Okay. Yeah. So this is another easy problem. So they are asking about total magnification, and they have given the magnification of eyepiece lens, as well as they have given the magnification of objective lens, right? So that means ME into MO. ME they have given, what is it, 10. MO they have given 50. So 10 to 50, this will be 500x. This is the easiest one out of all the problems. So the total magnification will be 500x. Okay. Yeah, this problem I'm reading it for a yellow light, monochromatic light, and for as I said, for monochromatic light there is a single wavelength. Lambda is 580 nanometer. Source optical microscope having medium between objective lens and specimen filled with cedar wood oil, which refractive index is 1.5 and the depth of field is 0.976. Find the numerical aperture and subtending angle. Yep. So yeah, take 1 minute and try to solve it. I'll solve it afterwards. Okay, so we'll see this problem. So lambda is equal to 580 nanometer, and refractive index they have given. What are they asking? Numerical aperture and subtending, another thing, depth of field. That once the depth of field means, the formula for depth of field is Z is equal to n into lambda divided by numerical aperture square, right? This is the formula for depth of field. So here n is given, lambda is also given, Z is also given. So you have to calculate numerical aperture square is equal to n lambda divided by Z. From here you will get numerical aperture value, right? And once you get the numerical aperture value, numerical aperture is equal to n sine alpha, right? N value, you can same n value you can put it here, 1.5. this value is known, alpha you know, right? Subtending angle. So here subtending angle means, so here you will not report the total angle. Subtending angle means always from, remember, the angle from the normal, whichever your microscope, the extreme part of the microscope is making from your normal. So whatever alpha you will get, you will report that alpha. Okay, so from this formula you first calculate the numerical aperture value. Once you know the numerical aperture value, you put the numerical aperture formula here. You know the n value, alpha numerical aperture value will also get from here, and then you calculate the alpha, right? So this is another type of problem. So there will be, I think in assignment they are asking about depth of field. One problem will be there, another problem will also be there regarding the first problem that we did. And so magnification and the total magnification, distance of distinct vision, and this depth of field. These formula they might have given in the assignment. So these you can refer to these problems and then try to solve the assignments. Okay. And yeah, this is another I think one simple formula. Calculate the position of the image and its magnification when an object is held at 10 centimeter from a convex lens of focal length 8 centimeter. So okay, yeah, try for 1 minute, then we'll solve it. Okay, so we'll solve this problem. So they have given find the position of the image and its magnification, right? And what are the things they have given? Object is held 10 centimeter from a convex lens of focal length. That means they have given u is equal to 10 centimeter. This u is object distance. Then focal length of lens is 8 centimeter. So we know thin lens equation. Thin lens equation is 1 by f is equal to 1 by u plus 1 by v. So here if you put 1 by 8 is equal to 1 by 10 minus 1 1 by v. So 1 by v is equal to 1 by 8 minus 1 by 10. 45 minus 4, it will be 1 by 40. So that means v is equal to 40 centimeter. So here we have calculated v, but the tricky part is they have asked about the position of the image. That means I told you that why we are calculating VE plus FE in when we conducted when we did this problem. Here in one place we are taking VO minus FO for the magnification of the objective lens, but in for the eyepiece we are calculating VE plus FE for the magnification of eyepiece. Why? Because the direction is different. So same thing you have to take consideration in this case. Here U is positive and V is also positive. That means your both your image as well as your object as well as your image, they will be on one side of the lens. They will not be, the lens will not be like that. This is the object and this is the image. No, in this case what will happen? This is the wrong case for this one. If my lens is here, then my image will also be here, my object will also be here. Why? Because let's say I am taking this direction as positive. The object is situated 10 centimeter and my image is situated in the same direction 40 centimeter. So this is what the tricky part is. The position of the image you have to clearly mention. If you are writing, then the position of the image you have to mention that they are on the same side of the object, as the same they are as the same side as the object from the lens. That you have to mention. Then you can calculate always magnification is given by V by U. So V is 40 divided by U is 10, magnification is 4. Okay, here this is the tricky part. Then I think we'll come to the this is the last problem. Okay, here there this is I'll explain this image. So here there are two mediums. One is medium is 1.33, another medium with refractive index is 1.5. Here refractive index is 1.33. So there are two medium through which our wave is passing, and the thickness they have given 2.02 micron, and they are asking calculate the optical path length difference. So we know that the path length difference, I told you that should be equal to lambda, right? When I derived the resolution limit for our microscope, we have derived that thing. Here they are asking it in a different way. Let's see whether we'll be able to solve it. I'll solve it. You try it first, then I'll try to solve it. So the optical path length difference they are asking. Okay. Okay, so we'll calculate the optical path length difference. So it is nothing. I don't think it has been covered. So the optical path length difference is defined as the product of thickness through which it is traveling, thickness of the medium through which it is traveling, and difference in refractive index. Okay, if you see, then thickness, what is it given? 2.02 micrometer, and refractive index is 1.5 minus 1.33. So you will calculate the value. So that is what called as optical path length difference. Okay, so I hope all of you have gone through these sample problems, and this was the last sample problem, and I think there are 10 problems have been given, and the deadline is 5th of February. Try to solve all those problems before that and submit it, submit the assignment, so that they will be graded. And yeah, if anyone has any doubts or anything, you can ask me, or also you can, I'm writing my email address. You can ask in the discussion forum as well, because I have seen one person has asked in the discussion forum. You can ask there. I will try to answer those questions here, or I will try to answer those questions in the email itself, or you can separately write to me. So this is my email address. It is sabyasachi.spd@gmail.com. You can write to me here in this email address. I remember one person asking in the discussion forum about a question, and that question is yeah, why C is equal to, I think he asked about nu into lambda. Yeah, so he asked why, if the frequency is decreasing, then why the wavelength is decreasing, or he got confused between that. Actually, the in video the professor has told that the frequency is unaltered, so I think he mistook that thing. The frequency is unaltered, and why the frequency is unaltered in this case, if I am saying why the frequency is unaltered of a light, because the frequency does not depend on the medium. Okay, the frequency does not depend on the medium. The frequency depends on the source from which it is coming, the light is coming. If you are changing the source, then only the frequency will, this is new, then only the frequency will be changed. If you are not changing the source, generally for a microscope which we are using, we are not changing the source, we are doing a different combination of objective lens, condenser lens, we are changing the height of the object where we are keeping, those things we are changing, we are not changing the source. So that is why this nu will be unaltered. In that case, if you are decreasing the lambda, if you are decreasing the lambda, then what you are decreasing, if mu is unaltered, if you are decreasing the lambda, the speed of light in that medium will be the speed of light, or the speed of light in that medium will be decreasing. And if we are decreasing the lambda, what will happen in energy thing, hc by lambda, so it will also be means the energy of course will be remaining constant, because according to C the lambda will also be decreasing. So the energy will remain constant, but in this case the speed of light that will definitely decrease. That's what I think he got confused, and he has asked in the discussion forum. So yeah, so I hope all these things are clear now. Okay, so is anyone having any questions or any doubt? They can ask me.
Yes, sir. It was nice class. One thing is, can you share that PPT, sir? Is it
This
possible?
this one.
Yes, sir. Yes, sir.
Yeah, I'll upload it in the. I think I have to give it to the team. They will upload it for sure.
Okay, sir. Okay. Thank you, sir.
Yeah,
Sir, to find that sine and sine inverse
yeah. Which sign inverse?
in the problem, sir, in the problem, if I want to find sine values,
In which
in
problem?
this problem we have to find alpha, no, sir.
Yes, yes, yes.
So it becomes sine inverse, no, sir.
Yes, sign inverse.
So to find that value, can we use the calculator, sir?
Yes, you can use the calculator.
Okay, fine,
Yeah,
sir.
yeah. All these problems you can use the calculator without, because there are angles involved. Without calculator you
Yeah.
cannot do. So you can use the calculator. No
Okay,
worries.
sir. Thank you.
Yeah. Any other question? Okay, if not, then we'll be closing the session. Thank you all for attending the session. And if you are uh, if you are still I recommend you to go through these lectures once again, all these problems, and try to solve the assignments and submit it. And if you are having a doubt at any point of time, you can write it to me, or you can put the doubt in the discussion forum, either me or the professor, someone else, someone will be answering to that. And yeah, so that's all from my side. And yeah, I wish you a happy weekend. uh, you
Thank
can,
you, sir.
yeah, you
Thank
can
you.
leave now.
Sir, can we see these lectures once again on the NPTEL website?
Just NPTEL website. No, in the NPTEL website, I don't think it will be available. But I will be separately uploading all these documents, as well as all these lectures. I'll be giving it to the team. I think they will inform you regarding that. I have recorded the lecture, so I'll put it in some link they have to ask me to put. I'll see, and if they share it with you, then that's fine.
Yes, sir. Please, sir.
Yeah, yeah, sure.
It will be helpful for solving the all assignments and all problems.
Yeah, yeah, sure. I'll check, and I'll upload it. I
Yeah,
think
sir.
the presentation they have asked me to upload. I'm not sure about the video, but I have recorded the video, and I'll give you the link in that case.
Yeah, sir. It's request, sir.
Yeah,
Thank you, sir.
yeah,
Thank you.
yeah. Welcome.
Hello, sir.
Yeah, please.
Yeah, the session was good actually.